Life on Mars might already exist. Not little green aliens, not ancient fossils buried deep underground, but microscopic warriors thriving in conditions that would kill you in seconds. Scientists have found organisms on Earth that laugh at impossible odds. They survive boiling acid. They endure frozen wastelands. They even handle radiation that would turn your DNA into confetti. And here's the wild part. These tiny survivors could teach us how life might exist on the red planet right now, or how we could bring it there ourselves. Let's talk about extremophiles. These are organisms that don't just survive extreme conditions. They actually prefer them. In 1977, scientists discovered something that shattered textbook biology. Near volcanic vents at the bottom of the ocean, 2 miles down where sunlight never reaches, they found thriving ecosystems. The water there reaches 750 degrees Fahrenheit. The pressure would crush a submarine. Yet bacteria were partying like it was the best real estate on Earth. These thermophiles, or heat lovers, changed everything we thought we knew about life's limits. But they're just one type. Psychrophiles love the cold. Halophiles thrive in salt that would pickle any normal cell. Acidophiles swim in battery acid for fun. And radio-resistant organisms? They treat gamma radiation like a light snack. One organism stands above the rest, Deinococcus radiodurans. Scientists call it Conan the bacterium. This microbe can survive radiation 3,000 times stronger than what kills humans. Its DNA gets absolutely shredded by gamma rays. Imagine taking a book and ripping out random pages, cutting others into confetti, then mixing it all up. Deinococcus just puts it all back together, perfectly, within hours. It has multiple copies of its genome and repair mechanisms that work like the world's fastest puzzle solver. But here's what makes it Mars relevant. It can also handle extreme cold, drought, and vacuum conditions. In 2007, scientists stuck it on the outside of the International Space Station. For 18 months, it faced the full fury of space. Cosmic radiation, temperature swings from minus 250 to plus 250 degrees Fahrenheit. Zero atmosphere. When they brought it back, still alive. A bit annoyed, maybe, but alive. Now let's talk about what these microbes would face on Mars. The red planet is not friendly. Average temperature, minus 80 degrees Fahrenheit. That's colder than Antarctica's worst winter day. The atmosphere is 95% carbon dioxide and thinner than Earth's by 100 times. Standing on Mars without a spacesuit, your blood would literally boil, not from heat, but from the low pressure. And the radiation, oh, the radiation. Mars has no magnetic field like Earth does, no ozone layer, so cosmic rays and solar radiation just slam into the surface unfiltered. You'd get your yearly safe dose of radiation in just a few days. The soil is also loaded with perchlorates. These are toxic chemicals that destroy organic molecules. Think of them as microscopic bleach for anything biological. NASA's rovers have found them everywhere, but here's where it gets interesting. The surface of Mars is brutal. Underground? That's a different story. Scientists believe Mars might have liquid water deep beneath its polar ice caps. In 2018, radar data revealed what looks like a subglacial lake under the South Pole. It's about 12 miles across, sitting under a mile of ice. The water stays liquid because of pressure and dissolved salts, kind of like how salt keeps ocean water from freezing easily. Here on Earth, we've found life in similar places. Lake Vostok in Antarctica sat isolated under ice for 15 million years. When scientists drilled down, they found thousands of species of bacteria. If Mars has these underground pockets of liquid water, they'd be shielded from radiation, protected from temperature extremes, and possibly rich in dissolved minerals that microbes could use for energy. The conditions would be similar to deep Earth environments where extremophiles already thrive. So how would microbes actually survive there? Let's break down their toolkit. First, sporulation. Many bacteria can form spores when conditions get rough. Think of it like going into suspended animation. The spore has almost no water. It's wrapped in protective layers. Metabolism drops to basically zero. In this state, bacteria can survive for potentially millions of years. Scientists have revived spores from 250-million-year-old salt crystals. Second, biofilms. Bacteria don't live alone. They form communities wrapped in protective slime. This matrix shields them from radiation, desiccation, and chemical threats. It's like building a tiny fortress. Third, DNA repair. We mentioned Dinococcus, but many extremophiles have souped-up repair systems. They can fix hundreds of breaks in their genetic code. And fourth, alternative metabolism. On Mars, there's no oxygen for normal respiration, but microbes could use iron, sulfur, or methane instead. Some Earth bacteria already do this in deep mines and ocean sediments. Scientists aren't just theorizing, they're testing this. The Mars simulation chambers at NASA and ESA recreate Martian conditions exactly. Low pressure, CO2 atmosphere, extreme cold, UV radiation, the works. Researchers put various extremophiles through this gauntlet. Methanogens, which produce methane, survived weeks in these chambers. Cyanobacteria, which photosynthesize, stayed viable in Mars-like UV exposure when protected by just a thin layer of rock. Lichens, which are fungi-algae partnerships, actually thrived in some tests. And salt-loving halophiles, they handled the perchlorates just fine. Some even used them for energy. There's even a proposal to send microbes to Mars intentionally. Not to contaminate it, but to test survival in real Martian conditions. Tardigrades, those microscopic water bears, are top candidates. They've already survived open space exposure. Mars might just be their next vacation spot. Why does this matter? 3 reasons. First, if Earth microbes can survive on Mars, then maybe Martian microbes already exist. The planet was warmer and wetter billions of years ago. Life could have started there and adapted as conditions changed. Second, planetary protection. We need to be careful not to accidentally contaminate Mars with Earth life. If our microbes can survive there, they could confuse the search for native Martian biology, or worse, outcompete any native life that exists. NASA sterilizes all Mars missions, but nothing is 100% sterile. There are likely Earth microbes on Mars right now. Third, terraforming. If we ever want to make Mars habitable, microbes would be our first colonists. They could produce oxygen, break down toxic compounds, and enrich the soil. Cyanobacteria could start photosynthesizing, slowly building an atmosphere over thousands of years. It's a long shot, but extremophiles make it scientifically possible. Life is tougher than we ever imagined. Extremophiles have shown us that biology doesn't quit easily. These microscopic survivors push the boundaries of what's possible. They live in places we once thought were completely sterile. And they're rewriting the rules for where we might find life beyond Earth. Mars might seem dead from the surface, but beneath the ice, in protected pockets, or even in the salty brines that sometimes appear, life could be hanging on, not building cities or sending radio signals, just quietly surviving, doing what life does best. And if not, well, maybe we'll be the ones to bring it there. Either way, these tiny microbes are teaching us something profound. Life finds a way. Even on a frozen desert 140 million miles from home, if this expanded how you see the possibilities of life in the universe, you know what to do.